Okay, so electric field. We started off last time with Coulomb's law. Okay, and Coulomb's law was that the electric force between two objects is equal to K, which is our electric force constant, times the charge on one object times the charge on the other object divided by the distance between them squared. All right. So this is just between any two objects in particular. However, a lot of times you have a single object that has an electric charge on it, and you want to see what its effect is like in the area around it, and that area around it is called the electric field. So instead of using this as the force with the two objects, we can assume that we're going to have a what's called a test charge. Okay, this test charge will always be positive. Okay. It's always positive. Okay, and it's always very small. It's just barely strong enough to it's so small that it won't have an effect on what's producing the other side of the electric force. And so what this test charge does, okay, is we're going to have this, I'm not going to make it negative, we'll make it positive. We have a positively charged object in the middle of some region of space. And if I put our test charge right there, okay, remember it's positive, what's going to be the direction of the force acting on it, on this guy right here? Where's it going to go? Okay, if this is a positive charge, it's going to go that direction, right? Okay, then if I put another one here, it's going to go where? What? Yeah, well, sort of.
Like the other way?
It's going to go away from our central charge. So if I put another one here, okay, this is really close, so it's going to have, a longer vector. Okay, if I put one way over here, okay, it's going to have a smaller vector, right? Okay, so imagine that you keep doing this over and over and over and over again, yeah? What happens is you start getting these lines that are coming out these lines start coming out from our central charge. If we keep moving our charge, we see that the direction of the force, no matter where we put our test charge, is always going to be away from our central charge. All right, and collectively, this whole thing is called the electric field. All right. Okay, we have something similar to this. If you guys remember, remember way back to last semester where we had the force of gravity was equal to G m1 m2 over r squared, except this was always attractive, so it was actually a negative because it always two massive objects always pull towards each other. Well, you could do the same thing. So if you have, a massive object and you put another mass here and here, they would all be pointing towards the center of the other one, right? That makes sense? So that means this region of space would be the gravitational field. Now you guys have listened to enough sci-fi that, we've entered the gravitational field of the planet, Captain. That sort of thing. That's that there actually is a gravitational field. That's what's happening. Okay, and it happens when really massive objects affect the gravity around them. Okay. We here, close to the planet of the Earth, close to the planet Earth, experience this gravitational field, but we experience it really close to the surface of the planet. The value of the gravitational field would be as if we divide both sides by our mass. Okay. Well, if this is the force of gravity divided by our mass, and we know that the force of gravity equals, oh, thank you, Todd. Force of gravity equals mg, right? Well, if we divide by m, this g all of a sudden hit menu. There you go. There you go. Hit menu again. Okay. So we've got the same thing here. We have our force of gravity equals this. But if we divide it by our mass, down here, that means that g is equal to this g m1 over r squared. Or, okay, the strength of the gravitational field near the surface of the Earth is equal to 9.8 meters per second squared. Yeah? That makes sense? Okay. It's the same idea over here with an electric field. That, in fact, the actual value of it would wind up being an acceleration, okay, of the electric field, but we don't refer to it as an acceleration. But the idea is that this is the strength of the force based upon how close you are to this object per unit charge that's in the field. So if I double the test charge, we're going to have double the force, right? If I cut the test charge in half, then we're going to have half the force. Yeah? Or if I change this value, we're going to have half the value. You guys following here? Okay. So this is the idea of electric field. Okay, so this is if we have a positive charge. If we have a negative charge, and I bring a positive test charge next to it, what's the direction of this force going to be? This is going to want to accelerate in what direction? If this has got a positive charge, this whole thing's negative. Remember, test charges are always positive. This is going to go towards that, right? Okay. And if I'm way out here, it's going to go towards, but not as fast. As if I'm in here, it's going to towards, but faster. Yeah. And so these same lines exist. They're in the same. They're still radial out from our charge, but in this case, they're all pointing towards our negative charge rather than away from our negative charge because of the change in the charge. All right. So remember, these fields are where our positive charge is going to go. What direction is it going to travel if it's in that place and part in space? Okay. We'll get more into that when we do on Monday when we talk about field lines. Okay, and you guys will be drawing them. But that's not necessarily what we're working on today. This, okay, bring us back up here. If this is our electric force, okay, then our electric field follows the same thing, where we would divide by our charge. Okay, electric field is E. Okay, E is our symbol for electric field, and it is equal to K Q on the big charge divided by the distance squared. So it's pretty much this. It's very similar to force, except it's with only one of the charges. Okay. Then all the same sort of things apply. If we double this charge, what's going to happen to our field? Okay, it'll double. If we double the distance here, what's going to happen to our field? It'll shrink. If we double this, we'll divide by 4 here. Yeah? Because if we double the distance, it changes with the square of the distance. So if we double the distance, it's 4 times less powerful as we move away. Okay. That's pretty much it for electric fields for today, and you guys are good to go on your work. Okay, real quick addendum to that lecture. You're probably going to be asked, what is the force on an object that has a particular charge? So if we have a field, if this right here winds up being our field, then our force on our object is going to equal to the charge on the thing that's in the field times the field itself. Okay, so our force is equal to coulombs times our field, and our field is in terms of newtons per coulomb or volts per meter, but you don't really need this one yet. We need newtons per coulomb. All right, so it's our force per unit charge, and if we multiply it by the charge on the thing that enters the field, then you're going to get the force on that object. Okay, so that's what you're going to need for your homework tonight.